The premise for this session, so I've been troubleshooting TCP since the 90s. Been through many phases of thinking, wow, I got this. I understand it. And then I come across a scenario where it's like, oh no, what I thought I knew didn't work anymore. It's like reality changed. And what I found is you often have to consider both sides, the sender and the receiver, and be thinking half your brain on sender, half your brain on receiver to make sense of things, to really like make the best sense of things. So both of the endpoints are truly independent. They work autonomously, but they're also influenced by each other. The sender can influence how the receiver can influence how the sender behaves and vice versa. And whenever you have high latency in the path, and I put high in parentheses because it doesn't have to be super, super high. I mean, you could have 100 milliseconds and the behavior would be different than if you had 40 milliseconds. So that's the premise for this class. My goals are we're going to compare and contrast endpoint behavior. We're going to look at a client capture and a server capture for the same conversation. We're going to drill down into what is it doing, and more importantly, why is it doing what it's doing on each end. We really want to challenge that. We're going to promote Wireshark profile features. Yay, profiles. If anybody was in my class yesterday, you know I love profiles. We're going to share experience and ideas, and I'm also going to expose you to some visualizations that will help reinforce the behavior that we're seeing. That's my goal. So I did the screenshots with 2.6.3. There's now a 2.6.4 that's out, but it was too late for me to redo all the slides, so 2.6.3. We have two endpoint captures. We have Wireshark profiles we're going to use, and the visualization tool is listed there. A little bit about me. If you saw this yesterday, nothing has changed since yesterday. I still love troubleshooting, and I did shave my beard off in 2003, and I love your beard, by the way. So my ask for you in this session is please engage, participate. We're going to be digging into some really tight details, zeroing in at the sub-micron, sub-particle level. Some of what we see is going to like, wait a minute, how can that be when this is that? And it's going to be confusing, contradictory. At least for me, I find it that way. You might as well. Or you might just say, oh yeah, I get that. That makes perfect sense. And which is good. Please ask questions. And then depending on how much time we have, I'm going to also ask you to question the answers. Right? The more we can really challenge how well we understand some core principles, the better we leave the room with like, aha, I think I got it this time. So we will end on time. That's my goal. I always aim for that. So we'll do as many of the questioning answers as we can, but I'll still try to keep us on track as well. So let's get going. So the application scenario, we have an HTTPS web application. It just coincidentally happens to be an app that I use to control capture agents. So WinPCAP capture agents running all over the place. I use the web app to start and stop captures and download captures. I don't have a private key, so we cannot decrypt anything. So we're not going to see any HTTP headers. It's all SSL traffic, which really is almost like saying it's all layer 4 traffic because we can't see what's underneath the covers. I had captures running on my laptop and on the web server. So the symptoms we're going to analyze, downloading capture files takes forever. Like, it's never just a little bad, is it? It's like, oh my God, it's a disaster. I can't get my work done. It takes forever. That was the case here. It took 16 seconds to download a 1.4 meg file, which when I'm in a hurry, that feels like forever. All right? I've isolated the connection to one TCP, or the transfer has been isolated to one TCP connection. I'm thinking about the next time presenting, I'll have a different course of how did we do that? How did we get to that one connection? Because that's probably a good hour discussion or could be if we explore a lot of details. So we're going to spend our time looking at port 52942, talking to the server. So of course, it's a very simple topology, right? My laptop, web server, life is easy. Nothing in between, right? Anybody believe that? No? So this is what it really looks like. My laptop, VPN client on my laptop, Global Protect from Palo Alto, talking to a VPN concentrator in New York City. So I'm in Southeast America in Florida. Let's see if I can get the pointer to work. There's the pointer. Okay, so up to New York. That's the first leg of the traffic. Then I think it's actually IPsec from me to New York, and then some kind of tunneling through the internet, lots of ISPs over to a gateway in San Francisco, where we come out of the tunnel, and then I show up on the web server. So there's lots of nastiness in between, and of course, there's all kinds of things in this cloud, there's all kinds of things in this cloud. We might hop from one transit AS to another transit AS. But it's my laptop talking to the web server. So this is the background of the actual topology. Are you ready for your first quiz? I love giving quizzes, as you guys saw from yesterday. So let's go for it. If you know the answer to this, don't shout it out yet, please. Okay, so the question is, what parking slot is the car in? Can you do the math? And I was going to have some music, you know, like Jeopardy. Bum, 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 bum. Anybody feel like they got an idea? You got an idea? Good, okay. Let me flip the picture around from a different perspective, because perspective matters, and that's what we're here to talk about. So now, what parking lot are we in? Or slot? Did you have it? 87? Okay, great. 87? Number, okay. So the idea is our perspective matters. And when we're looking at client capture versus server capture, knowing which direction we're looking at, which endpoint we're looking at matters. So the endpoint behavior, each one can be unique, and I want to stress they are independent, but they're also influenced by the other end. We can't forget that. If we forget that, then it's like, okay, what I'm looking at doesn't make any sense. Each side, the TCP stacks make decisions about timer values, about the health of the network, about what's arriving, how to interpret it. And then, of course, there's third-party actors that can also affect the behavior. Proxy servers, VPN concentrators, firewalls, IPSs, you name it. So we're going to get in now to our split brain comparisons. And the idea of the split brain is we're going to focus on what does the client think, what does the server think, why do they think what they think. And it's a little aggressive. I don't know that we're going to get all of this done. In fact, I know the last one, I purposely moved it after the thank you slide, so it'll be for later use. But we're going to start with very, very simple, and then get into somewhat more complex, and then it'll be like really complex. So we'll look at the three-way handshake, we'll look at latency. We're going to compare and contrast the Wireshark expert info for both captures. So you can see how does Wireshark interpret what's going on. Then we're going to jump into the meaty part, fragment overlaps, which is a Wireshark expert info condition that it calls out of sequence packets and packet loss. And then we'll look at bytes in flight. We'll compare that, server side, client side. And then congestion is a bonus section at the end. I'm pretty sure we're not going to have time to get into that. But if we do have time, we will. Okay, so let's start with our first comparison. And when I told my boss that I was going to do something called split brain comparison, he goes, oh, it's like Shakespeare. So he inspired me with the Shakespeare picture. This part's super simple, right? We're just going to look at the three-way handshake, and we're going to compare what each side tells the other. So we're looking at the client capture. Notice the arrow up in the top left-hand corner. We're looking at the client capture, and we're seeing that here's what we're advertising back as we open the connection, right? So of note is what's our maximum segment size, 1360. We do have window scaling enabled. So we could go as high as a really big number for a receive window, and SAC is permitted. And now let's look at the server side. So the server side, and notice in the top left-hand corner, I've tried to make sure that the file name is present on every screenshot so that when you're looking at it, you can easily see, right, this is the server capture versus the client capture. So it's a little bit different from the server side. Really only the maximum segment size is different. Instead of 1380, it's 1460. But those two numbers will come in handy a little bit later because we're going to see some differences coming up in what the traffic actually looks like. But three-way, I always emphasize to start with the three-way handshake because you need to know what options are present, right? And what the segment size is, et cetera. Okay. That was our first comparison, right? Easy peasy. Hopefully that's something that you tend to do if you can get both captures and pay attention to what's being sent on both sides. And by the way, because there's equipment often in the middle, it is possible equipment in the middle can change those settings. Right? So that's why the endpoints, it's nice to know, and then see what shows up on the other side. Okay, so we have our red-green brain. We're now going to look at latency differences from each of the capture standpoints. Again, this one is going to be pretty straightforward, but it'll help us as we dive in a little bit more detail. So from the client capture, and you can see the file names up there again. From the client's perspective, the client says, geez, for this handshake, for the three-way handshake, seems to me the latency round trip time is about 121 milliseconds. From the server side, at the point in time when he's processing his three-way handshake, which is milliseconds different, he's saying, well, it looks like it's 129 milliseconds. It's not a big difference. And the importance about this is not that it's big or small, is that it is different and that it's constantly changing throughout the life of the session. So yes, you can get a reasonable idea of round trip time by looking at the three-way handshake, but please remember that it can change, it can get longer, it can get shorter. So my question to you guys is, if it gets shorter, what does that tell us? So routes could have changed, or the well, and I'll just generalize that the profile of the network has changed a little bit. Maybe utilization has gone down, maybe device queuing has gone down, maybe there's been a complete reroute. But the point that I'd like you to walk away with is the lowest number that you observe in the life of the capture is probably the most accurate representation of true latency. Like how long, the speed of light to get from point A to point B. Anything above the lowest number is some sort of additional device effects, like congestion, queuing. So I'm going to pause there for a minute. Is anyone not comfortable with that? Because I can say it again. So the worst case tells you it was bad, but it doesn't tell you what good looks like. Like if you wanted to know what is the true latency, it's the lowest number observed during the capture. And we'll look at some examples of that coming up from both endpoints. Wireshark does maintain a derived metric called initial round trip time. And you'll see it in the TCP section down here. It's kind of a reminder of what Wireshark thinks was the initial round trip time. And notice it's a tiny bit different than the actual deltas shown on the screen there. So the delta is like 121.49. IRTT is being recorded as 121.57. Okay. So on to visualization, because as we go into the deeper comparisons, it's going to be helpful to kind of show traffic moving from one side to the other over time. So if we could visualize the traffic, we'd see traffic bouncing back and forth. We'd get some sense of the frequency of traffic. Like, is it 10 packets a second? Is it 100 packets a second? Is it 1 packet a second? As well as the density. It's like, is it a whole bunch all streamed together, or is it spread out over time? And then the duration of when things are happening. And ideally, if you could put some expert analytics with that picture, you'd get a sense of, oh, this was a retransmission, or this was a dropped packet, or this was out of sequence. Some sort of label that helps to visualize what's going on. If only there was such a capability. If only. But there is. So this is a tool that I use at work, which is a wrapper around Wireshark. So this will not work without Wireshark. Wireshark is essential for this tool that I use at work. So a quick orientation. First, if you'll notice, there's a file name up at the top. So this will help us keep track when we're going to flip back and forth between the Wireshark decode view and the visualization. And in both cases, I've tried to keep the file name present. So the swim lane that you see in the middle shows the client at the top of the swim lane, the server IP at the bottom of the swim lane. So think of those as the sync points of when packets are arriving or when packets are being transmitted by those hosts. So the top line is client, bottom line is server. Time is going from left to right. If you select, and we'll have some examples of this, if we select an arrow, just click on the arrow, the packets represented by that arrow show up in the bottom in a traditional summary decode. And we also have a concept now of 2 times for every packet, a send time and a receive time. And this is one of the most important attributes of being able to kind of split your brain into what's happening on both sides, is to think about, hey, there's something I know, it's either the send or the receive time, and then there's something I don't know, which is the reciprocal. And we'll look at that in a little bit more detail. So let's talk about estimated times versus actual. We can be sure that when we're looking at a capture, that capture and the timestamps are 100% confident. We're 100% confident that when I see a packet that is being transmitted out, that's the time it left. And when I see a packet come in, we're 100% confident that that's when it arrived at the host. Does everybody agree with that? Yeah? So using what we do know, we can estimate what we don't know. So if I know a packet came in and I have an idea what the latency is, I can make an estimate of when it left the other side. And if I know when a packet leaves, I think I have this on the next slide. Yeah, so when we receive a packet, and I want to emphasize, it's a reasonable estimate. It's not necessarily 100% rock solid, but it's a reasonable estimate. So if we know when we receive something, we can make an estimate of when it left the sender. And when we send something, we can make a reasonable estimate about the time that it was received by the receiver. So here's an example of that. Again, we're looking at the client capture. So this is times recorded by the client capture. What we do know for sure is when things leave and when things arrive. And then we can estimate the other end. I want to call it the reciprocal time. It's not a great name. I'm looking for a better name. But it's the, if I know the send time, I can estimate the receive time at the other end. If I know the receive time, I can estimate the send time of the other end. So this is what we're going to use as a tool to look at both sides and the behavior as we drill into more details. This will be one of our visuals.
John, are you assuming that the same route will be used in both directions?
No. No assumptions about the route. Okay. Yeah. And by the way, to the point earlier about the route can change, it could change during the session for sure. Okay, so now what we're going to do is see how we can use the visualization that we just looked at to understand TCP state details during the life of the connection. And we'll start with just the three-way handshake. So how many people have read RFC 793? We got 1, 2, some 2.5, 3, 4, 5. I mean, it's a classic. You got to admit, it's the granddaddy. It's one of the granddaddies of RFCs. It is a classic. It's important to understand some of the details. It's been revised numerous times, so you kind of have to say, well, some of this may have been modified. But are you guys familiar with the three-way handshake state machine? Right? Each TCP is in a certain state depending upon what's happening in the connection. So closed, listen, those are pretty straightforward. Send sent, send received, established, etc. So we're going to use these now with the visualization to ask some questions about what state is each side in during the three-way handshake. So we have a little icon here with a stopwatch and a point in time. And what we want to ask is, at this specific point in time, what's the state of each endpoint, starting with the client? So from the client perspective, what state are we in at this particular time of the transfer? Send sent. Cool. At this time, what's the state of the receiver? Listening, right? So the receiver has no idea anything is coming his way, right? But the client says send sent. Perfect. Let's look at it. Let's keep the progression going. How about at this point in time? Client side? Send sent. It hasn't changed, right? Because he doesn't know anything different. And now on the server side? Send received. Right? So we kind of have a half-open connection at this point, not fully open. How about at this point in time, and it might be a little hard to see, but I'm trying to note that that arrow point is when that packet actually arrived back, the SYNAC. So I'm trying to denote like right there. So what do we have now on the client side? Established. And what do we have on the server side? Received. It hasn't changed on the other side because he hasn't heard anything back yet, right? So now we've got two different states again on both sides. How about now? Any change? Same, no change. So the green line has some payload. How is it that the client could send payload? And I can tell by the color, by the way. It's a visual thing. One of the attributes is the color. So the green line says there's some payload above 500 bytes and below 1,000 bytes, or up to 1,000. So there's payload that the client sent, in theory, before the connection is open on both ends. So my question to you is, what happens if that green line arrives before the red line? Just take a guess. Say again? No, these are two different packets. One is the ACK and one is a data packet. Because as you guys pointed out, the client says, hey, I'm established. I'm going to send some data. The server is still in send received state. So if that data packet were to arrive in advance, he'd have to say, whoa, we're out of sync, and maybe issue a reset. So hopefully it arrives in the order that we see. We see them arriving in order, which is good. So we're not, for those of you who were with me yesterday for the SAC extravaganza, we're not going to dive into craziness like that. This will be pretty well behaved. Okay, let's keep going. Now what do we have on both sides? Established, established. And notice that the green arrow point is just to the right of the time that I'm looking at. So the client knows, hey, I've sent some data, and the server is just about to receive it, but he hasn't received it yet. So that's that time point right in the middle. So quick question, do you guys, when you're working on Wireshark captures, do you currently think about what happened on the other end at what time? Is that something? So I've got some yeses, some maybes, another yes, I got a yes, which is good. And then how about the state? Do you think about each side's state? What state am I in? What might be in my transmit buffer? What might be in my receive buffer? The reason I'm bringing this up is because those details help to reinforce our understanding of what should be happening, could be happening, might be happening when we're looking at really strange conditions. By the way, nobody asks us to look at captures when everything is working fine, at least in my experience. Anybody do that for you? Say, hey, it was a great day yesterday, response time was wonderful. Could you take a look at the captures and see what's in there? I mean, everything was so good. We were so productive. Nothing failed. They never do that, do they? It's only like, you know what? It was really bad yesterday. And you say, well, what time was it? And they say, oh, it was the morning. Well, what time in the morning? Oh, I don't know, sometime between 9 and 11. Oh, can you be more specific? No, I'm not really sure. Okay. Anyway, we only look at captures when something's broken, in general, unless we're trying to, do some sort of a study, a technology study. So we've just started on this little journey, we're 30 minutes in, around looking at both sides of the connection. So let's keep going. So now we're going to look at the expert info captured from two instances of Wireshark, one looking at the client capture, one looking at the server capture. Here's the client, here's the server. I'm going to put them both together side by side. Now the numbers here are the server, and the numbers here are the client. We'll have to talk about the red bar because you can't tell from this screen, but they're two different red conditions, but we'll look at both of them. But here's a side-by-side comparison where there's some disagreements about certain conditions based on what the expert analysis engine found in each capture. So they definitely agree. Let's talk about what they agree on first. They definitely agree that there was 35 keep alives. So they agree on that. That's good. We have some agreement. But they disagree greatly on out of order, previous capture, retransmissions. I'm actually a little surprised about the duplicate acts, that they don't agree on that. And it could, I don't know, remember this is 263. It might look a little different on 264. Let's look at these in a little more detail. So I've pulled out the retransmissions so we can talk just about the retransmissions. So my question is, why does the server report more than the client? Any thoughts about that? Say it a little louder, please.
Retransmission are lost between the server and the client. So one side sees more transmission, but the client only saw the last of the one or two retransmission.
So I think what you're saying is the server in the capture, so really when I say the server, Wireshark looking at the server capture sees the same segment more than once. Yeah? So we see it go out initially, and then for some reason we see it go out again. So we call that a retransmission. Yeah? So I just rephrased what you said a little bit. By the way, how does Wireshark define a fast retransmission? And the good news is, all you have to do is open the help window. Okay, and honestly, I didn't know that before I started on the course. I thought, well, let me just look at the help panel and see if it defines these things. And there it is. There's the definition for fast retransmit. And you kind of see it's a set of conditions, and it supersedes other conditions. So my goal for you is just to know, click on the help. There's great information in there. And it gets better and better with each release. And by the way, I was talking with Peter, the TLS developer, and he encourages us to not only give feedback on the behavior of Wireshark, but also the quality of the documentation. Right? If we see something in help that's confusing or could be worded better, they want that feedback as well. So please don't be shy about giving them that feedback. Okay, here's the opposite. Now we're looking at out of sequence, and now the client has more of those than the server. So why does that happen? And if you think about my class yesterday, because things are arriving, they're leaving the server in order, but they're arriving out of order for some reason. And remember my big ugly picture of Orlando to San Francisco, there's VPN concentrators and all kinds of good things. So curiously, why would the server report any out-of-sequence packets? And we'll drill into that a little bit more in a few minutes. But I found that a little bit curious. It's like, well, how come? Why does the server see out-of-sequence? Now, it could be data that's coming from the client that's arriving out-of-sequence. But we'll see. We're going to dive into that a little bit more. There's also help about what is the definition of out-of-sequence and how to interpret it. Okay, how about this line? Ignored unknown record. We had 128 on the client and 8 on the server. So why is it the client reports more SSL unknowns than the server? Say it again, please. Great question. If I had an F1 button right now, I'd grab it. So here's what it means to me. In order to interpret SSL, you have to put segments together into like the entire message, the entire SSL message. And to me, my guess is, and there's some good news coming in 2 slides, my guess is that when we're putting things together, but they arrived out of order, it makes it difficult for the SSL engine to put things back together. That's my guess. Let's look at the next one. We had 2 of these, and it only was reported by the client. Ciphertext length must not exceed 2 to the 14th plus 2048. That's a formula I hope I never have to remember. 2 to the 14th plus 2048. My suspicion is, again, it's the same result of things arriving out of sequence, and we can't put them together. So good news is coming. As you know, I did this with 2.6.3. I did talk with Peter Tuesday, about what I'm seeing in 2.6.3. He said, oh, please try it with 2.6.4 because we fixed the reassembly engine when things arrive out of order. And now we do a better job of the expert info does a better job of interpreting the SSL TLS. So I didn't have time to like redo all my slides. It's like, okay. So please use the latest version when you can. Unfortunately, I started this course in May, thinking, oh, I have until November. I've got time to like put it all together. And of course, the version changed since then. Right. Fragmentation overlap. Why does the server report fragment overlap error and the client does not? We're going to drill into this in more detail, but does anyone have a guess as to what it actually means? New fragment overlaps old data, retransmission, question mark. So we're going to drill into this. Go ahead. Could be MSS related, absolutely, good guess. I like that guess. And then the other question I have for you is, should this really be an error level notification? And we'll see why in a minute that we ask that question, and maybe we might submit a suggestion to the core developers to tweak that a little bit. But let's look at this in more detail. So before we leave, we're now kind of looking at differences client and server from the viewpoint of the expert engine within Wireshark. Right? So Wireshark came up, consumed the client capture, made its assessment. Another instance of Wireshark started with the server capture and made its determination based on what it finds. So clearly, we found different things in different captures for the same connection. Same connection going back and forth. Any thoughts or comments about looking at things this way? Is this like anybody's brain hurting? Should we not do this at all? Should we avoid this at all cost? I think as we go through a little bit more, you might see things you've not seen before, maybe. Or you'll see things from a different perspective. So let's keep going. So we're going to drill into one of these alert messages, and notice we're going to use the server side capture because this error only was flagged on the server side. And it's a great opportunity to do some more comparison. So we're going to drill down. So pop quiz, does anybody remember the name of this brain? Anybody watch Young Frankenstein? It's a classic. It's like RFC 793. It's a classic. So when the helper found the brain in the laboratory, all he could tell was Abby someone. He wasn't sure who. Abby someone. And then he remembered the last name was Normal. So it was Abby Normal. Anyway, it's just some fun. If you haven't seen, you have to see this movie if you have not seen it. It's a classic. Young Frankenstein, Mel Brooks. I'm sure it's on Netflix. Okay, pop quiz time. Ready? And for those of you who were with me yesterday, don't call it out just yet. What's one of the best things about Wireshark? Sorry? The developers. Yes, okay, the developers. But what else? And for me, it's the totally flexible columns, views, profiles. I mean, I can't say enough about how it changes the way I can, and the speed of analysis. So back to the help screen. I don't know if you guys have seen this. This is in 9.6.3. It might look different in 9.6.4. But there's a whole help section on configuring profiles. And I don't know if you realized it, but it's a combination of filters, columns, settings, preferences, colors. I mean, it's amazing. It's absolutely amazing feature. And it didn't cost any more than the download. So it's wonderful. So configuration profiles, I'm a big fan. We're going to use 3 during the session. When the presentation gets uploaded to the retrospective page, I'll have both of the captures, client and server, as well as these profiles that you can download. And by the way, did everybody know you can share profiles? Like with a team? I mean, that's amazing. Hey, here's my favorite profile. Start using it. It's a great feature. Okay, so if we drill into the server-side capture, what we're going to do is we're back to looking at fragment overlap. And what does that mean? Here's the classic view. But the classic view doesn't really help me. So I need some additional columns to kind of quickly determine where this overlap is. So think about what columns do we need in our view to better understand fragment overlap. What can I add to my view? What can I add to my profile? So here's my split brain sequence analysis profile. Notice we've got some new columns. We've got delta, added TCP length instead of packet length, sequence number, next sequence number so far. That's what I've added so far. Because of fragment overlap, we've got to find out where sequence numbers are overlapping between packets. But before we do that, something caught my eye when I got to this view. It was sort of in the classic view, but it didn't jump out the same way because the classic view is kind of scrunched together. Here, the columns are a little bit broader, they're centered, it makes a difference. So what are these jumbo packets all about? Any thoughts about that? I mean, they're bigger, they're not allowed, things shouldn't really be this big, or should they? Say it again? They are not jumbo packets, they are segmentation offload. Uh-oh. I'm getting feedback. Yes. Offload. Good. Large, it's got several different names depending on the vendor, the NIC card vendor. Like if you go to an HP NIC card, they'll call it large send offload. Other NIC card vendors as a feature might call it something different, but it's typically enabled on the NIC card. So this is an important piece of information that you'll need as you're troubleshooting day to day. When am I seeing large send offload? When am I not? So to help understand this a little bit better, a couple of questions. Where does WinPCAP get its packets from? Anybody know offhand? Just general? I'm sorry? Inside the OS, right? And my understanding is, and I never looked at the code, my understanding is as the message is being sent to the NIC card, I believe, we get, sorry? Before the NIC driver, yeah. So we see it moving through memory buffers, and we snag it, and then we grab it. So, but it's somewhere before it gets to the physical card. It's in memory someplace, right? So it could be before driver, after driver. Honestly, I don't know, right? Both cases are possible. What happens, what's the rest of the journey after we see it? So it eventually gets to the NIC card, and the NIC card has certain settings and options. Some of the simpler ones are like checksum. Do we want to offload checksum calculation? That's been around for years. Large send offload is an option that's been around, I don't know, 5, 6, 10 years. It's been a while. But the packet continues on through memory, eventually gets to the NIC card. And then I'd like you to think about how is that different on a virtual machine? On a virtual machine, there is no NIC card. It's a virtual NIC. So now I've got something that the virtual NIC might do, might not do. There's a driver for the virtual NIC, right? Before it goes to the real NIC. And that real NIC, the physical NIC on the ESX host, is supporting multiple VMs. Does that make sense? If you think, the reason I want you to think through this is the cause and effect of what we see in Wireshark can change for many different reasons, including what the NIC does, what the VMware system does, et cetera. And there's one more question. Has anybody heard of a blade server? Yes? So a blade server is, a chassis that has some NICs on the back. It may even have a switch in one of the slots, and then it has CPU memory blades and sometimes solid-state disk inserted into the chassis. The point I want to make is the blade itself does not have a NIC card. It plugs into the backplane, and now I have to get to the NIC card through the backplane. Another example of it's not always a direct stop from when we see it in Wireshark from PCAP to when it actually hits the network. And there's influences that can happen. And it's important just to keep that in mind. You don't have to remember all the details, just be aware of, hey, the server technology makes a difference. Last one, has anyone heard of this? TCP receive offload. This one is a little bit crazy. It had me chasing my tail for months, unfortunately. I'm not proud of that, by the way. In this case, the NIC card consolidates incoming packets and aggregates them, and then presents one big packet to the operating system. And when PCAP will not see the little packets, it'll see the aggregated packets. So what happens to the defragment bit? We don't know what they were on the little packets. We only know what they were on what got presented to the operating system. So be aware of large receive offload, LRO, as well. If you ever see big packets on the receiving side, it's either real jumbo packets that are legitimate large jumbo packets, or large receive offload is in play. So let's get back to our fragment overlap, because we have to understand what that is. And now that we've seen there's something called large send offload, or TCP segmentation. So here's our overlap. 714 was flagged as fragmentation overlap. And if we look at this number, 522835, this is the relative sequence number, we can see that it's somewhere in this packet of 2569. And let's see, what does that actually look like? So here's the overlap. When we retransmitted, we actually are covering two different fragments that were previously transmitted. So I didn't quite put it on this graphic, but there's another packet that is right here. And now this one fragment, this one segment covers both of those segments. So we have a fragment overlap, according to the Wireshark expert info. So back to my question of should it be flagged as a red error, this sort of looks normal if you consider that large send offload is enabled. So I'm not so sure this needs to be hair on fire emergency error. It maybe could just be informational and it would be good enough. So at first it seems odd. I've worked with people who've said, hey, this is the weirdest thing ever. There's this overlap between this retransmission and two previously submitted packets. And we thought it was something broken, but it turns out it was just large send offload. So you can be reasonably confident it's large send. Let's look at the client capture. So we're gonna anchor, we're gonna look for 521543 in the client capture. So we're back in the client capture now, and we can see that we have our file name. And notice that the packets that arrived at the client had a segment length of 1292. So we started with something big. I actually forgot the number now, but it was a big number. And what's arrived at the client is something smaller. So for sure, large send offload is configured on the server. And that somewhere the NIC is handling segmentation into smaller packets. So a few more things to look at here. So on the client side, the expert analysis said previous segment not captured. So why would it say that? And in order to figure that out, we kind of have to see what comes next. So we've got this concept of I see a state based on a packet, but really to understand it, I've got to kind of see what comes next. So let's see what comes next. Here's the picture of what the client sent, what the server sent and what the client received. Coincidentally, and for my convenience, packet 1000, easy to talk about, was the first one in this block that showed up. And then we've got 1277 bytes missing. And then this showed up, packet 1001. What's also interesting here is I've got 1292, 1292, 1292. Why am I missing 1277? I mean, I always find little things like that and go, why is that? Not that it's important, it's just odd to me. It's like, why isn't everything 1292? Why am I missing 1277? That's just the way my brain works. So we've got some other clues about this missing packet. So we can see, by the way, does this laser pointer show on the screen okay? Yeah? Okay. Here's our packet that arrived. Or actually, no, we're expecting 522.835. Instead, we got 524.112. And the expert analysis said, hey, it looks like the previous segment was not captured. At this point, we don't know, was it dropped or is it just out of sequence? We just know that we were expecting 522.835. We got something different than that. By the way, that's the one that was retransmitted on the server side. That's the one that we saw as the fragment overlap, was this segment 522.835. So we've got some other clues here to look at. Notice the change in the ACK behavior. We've got 2 packets that came in, we ACKed it. We had 1 packet come in, and then we immediately ACKed that. So what does that tell us about what the receiver thinks is going on? I'm sorry? Yeah, so there's probably some SAC involved as well, but that what we're continuing to receive is considered out of order because we're missing that first segment. So we've got a lot of out of order things to account for. Let's keep diving into this a little bit more. So I want to use a different profile now so that we can quickly see the SAC field. So there's a profile called SB-Seq that'll get uploaded. And you can see now that we have, in our columns, we still have sequence number, next sequence number, ACK, and I've added in left edge, right edge. It turns out that the info field at this point is really not that helpful anymore because there's no protocol information to see, it's SSL. What really matters for this effort is the TCP level numbers. So we can see, let's go back. We can see that data's coming in. Notice that the ACK continues to say, hey, I need 835, I need 835, I need 835, I'm waiting for 835, and you can see that the right edge keeps incrementing, saying, hey, I'm receiving data, and it's not the data that I'm looking for, but I am receiving data. So when you're looking at just the client side, and only the client side, you can see that, okay, I've asked the sender to retransmit something, but I keep getting more data coming at me that's not what I asked for. It keeps streaming in and streaming in. So why does the server continue to send the segments other than the one that we said we're missing? Because there's like 17 of them that got sent. So visualizing this can really help. If we look at a picture of traffic moving between the nodes over time, we can now see there's bursting of packets, there's ACKs, there's more bursting of packets, there's ACKs, there's our retransmission. We're going to drill into this in a little bit more detail to see if the visual view of this helps to understand what's actually happening. So if we look at our point in time like we did earlier with the triple ACK, which was pretty simple, right? It was just 3 packets. If we look at things now where we've got data in flight, we've got the sender has one view of the world, the client has a different view of the world, there's things in the middle of the network that are traversing. What can we say about what the sender's view of the world is? We'll start with the sender and then we'll go to the receiver. So if I were to say to you guys, what do you think the sender thinks about the network and the receiver from looking at this picture? Say it again. He's happy. Yes. Who said that in the back? Hi, he's happy, that's right. He's a happy camper because as the ACKs are coming in, he's immediately sending more data. So as soon as I ACK some data, there's some room now in my congestion window, I can put some more data on the wire. So ACKs come in, data goes out. Now, let's keep going. We're going to zoom into this picture a little bit in some detail. So you can kind of see the black line point in time. So notice that the thick blue line came in and an ACK immediately came out. Make sense? What it should do? Good. And then we're going to continue to go across the screen here. And we're going to zoom in now down here a little bit. We have an ACK come in, and then immediately, like we saw before, data comes out. So at this point in time, to use the description that I heard in the back, the sender is still happy. It's like, hey, I got an ACK, everything looks good. If I keep moving towards the left, though, and I do want you to kind of make a note here that we received an ACK here, but there's no data coming afterwards. That's kind of a visual clue. And by the way we're looking at this capture now is we're looking at both ends at the same time. We've used that send plus receive view to kind of draw a picture now of what's happening on both endpoints. So an ACK comes in, data goes out. This ACK comes in, data goes out. This skinny ACK comes in, data goes out. But this ACK comes in and nothing happens. That's a visual clue, and we're going to look at that in more detail. Okay, so the ACKs continue to go towards, so the data came in, ACKs continue to go towards the sender down here. And I want to look at what's happening right here real quick, which I think I have a blow up. Yeah. So if you see this line, this red line, which is a zero payload length transfer, so it's an ACK. There's one blue line that came immediately after this came in. So what would you presume that means from the sender's point of view? Well, so I received an ACK, and notice I've got one blue line that got spawned, and this is the retransmission of the missing packet. So this label here came from the analysis that said, oh, that's a retransmission. Let me put a label on it so we can see it. So this is the fourth ACK of the missing segment. So we have the original plus 3, right? Triple duplicate ACK. Is everybody comfortable that there's 4 of them? The original plus 3, triple duplicate. But then there's more things that come in. There's more ACKs coming in because they were already in flight at the time this came in. So we sent the missing segment, and then the sender stops. He's like, I'm going to have to hang out for a bit before I put more on the wire because I'm doing a retransmission, and for whatever reason, that particular TCP stack says, I don't think this network is as reliable as I thought it was. I'm going to slow down a little bit. So if we keep going. So let's flip back now into the decodes. First off, here's our missing segment. We're going to examine a couple of details. We're in the client capture. A couple of details about the segment coming in. First and foremost, take a look at the time. 107 milliseconds from the previous packet. Again, this is the client capture. So the deltas in Wireshark are relative only to the capture that we're looking at. So we're in the client capture, 107 milliseconds, and it kind of begs the question, why was there such a delay of 107 milliseconds? And let's see if we can zoom into that. So we're going to look at another feature of Wireshark. Did you know Wireshark has a lot of great features. There's actually a parade of features. Here is the Wireshark feature parade. I couldn't resist. This is a great time to use the time reference to double check this delay that we saw, this delta time. So we're going to set the time reference of, does that say ACK number 3? Yes. So we're in the client capture. We're setting the time reference of when did we send the triple duplicate ACK back to the server. So that becomes time point 0. Here's our retransmission down here. And now we can see that earlier what looked like 107-second delta, it's actually time-wise 116 milliseconds round trip to get from the client to the server to say triple duplicate ACK. And we saw visually when the server got that, he immediately sent the retransmission, and then he stopped. And then we got the missing segment here. But in the meantime, look at everything that got sent. If I can get my laser back. Look at all these packets that came in from the server before the retransmission. And in one respect, when you start looking at a capture, you go, well, wait a minute, we're missing a segment. Why isn't the server sending it to me? Why is it taking so long for the server to do that? And what we saw in the picture was there's lots of round trip times that we have to deal with and be aware of that explain that time delay. I would also point out that this time delta, I see what I'm doing wrong now. My left-right orientation, I think. There we go. Notice this round trip time is the lowest. This is lower than the three-way handshake, which gives me some sense that the true latency, this is a segment back to the beginning of the three-way handshake where we looked at latency. We saw 121, we saw 129, and I said that may not be the lowest. So far, this is the lowest. Right? So yes, there could have been a network reconfiguration, unlikely. I mean, it could be. But now we kind of get a sense of, hey, perhaps this is what true latency looks like, 116 milliseconds. This is a little bit of a segue from the retransmission. But being able to understand the round trip time is important because we've already seen a case where we stopped transmitting because we had to do a retransmit. We stopped sending payload. We had a delay, and it cost us time. In this case, it cost us 116 milliseconds. Anybody use the time reference set? Yeah, I mean, it's a great, absolutely great feature. So kind of going back, why did this Wireshark expert decide that this is actually out of order and not a retransmission? And I think the answer is because it's never seen it before. This is the first time it's seeing it. But for my own purposes, it would be nice for it to say, well, this is actually a fast retransmit, isn't it? Right? Because we sent 3 duplicate ACKs. It was immediately transmitted when the 3rd duplicate ACK got there. So really, it is a retransmit. So I need to see if 264 treats this differently. It might. So next question for you guys. Again, we're on the client capture. We just received the missing segment, which, by the way, did overlap. Remember, we started down this journey with fragment overlap? It did overlap with 2 other segments. So my question is, why are we seeing SAC when that missing segment came in? And if you'll notice, the SAC, how many bytes are there? The difference between... I should probably turn this way. The difference between the left edge and the right edge, how many bytes do we have there? 15, right? We sent a segment of 1292, but we're sacking 15. Any idea why? Why would the receiver bother to say that? And the answer that I believe, it's like, oh, by the way, just so you know, Mr. Sender, I've already received these 15 bytes before, no big deal, but just letting you know, right? Remember when we looked at the jumbo frames, or what looked like jumbo frames, and we saw it was large send offload? The operating system really has no idea what the NIC card is doing to chop up the frames. The operating system only knows, hey, I'm going to send you this segment, please get it there, thank you, do it well, reliably, and all of that. So we're going to now inform the operating system that, oh, by the way, we did receive 15 extra bytes more than once, just letting you know. It's not an error, it's really just more informational, just FYI. One more drill down, and then we're going to probably have to stop here. This time delta of 119 milliseconds, what does this tell us about bytes in flight and the congestion window? And we're back, by the way, to normal time. I removed the time reference. But the difference between this ACK, where we're saying, hey, I received the missing piece, and the next payload of 119 milliseconds, what does that tell us about what the sender thinks about the network? Remember, we saw the sender stopped. It has to wait. So the answer, if I'm hearing you right, is the sender had to wait for an entire round trip time to make sure that the retransmission arrived because it doesn't trust the network. Thinks it's unreliable, exactly. Right? So that's basic TCP congestion control on the sender side. What I was a little surprised about is I'm only missing one segment. Should it have waited? I mean, should it have stopped at that point, missing one segment? Why couldn't it have kept going? It seems kind of inefficient. What I didn't tell you is that this server is Windows 2008. It's an old Tomcat server, old Tomcat version. Doesn't affect TCP, but the Windows 8 would affect TCP. So we're looking at a fairly old TCP stack in this particular sender. So here's the delay of the round trip time. So it took, and this again is from the view of the client, right? Here's the 119 seconds. I sent the ACK. It had to travel across country through all the VPN equipment, the internet, et cetera, et cetera. It gets registered and arrives at the server. And now the server is happily sending a burst of packets. But the bytes in flight, at this point, when this ACK comes in, we're back to 0 bytes in flight. So we've kind of lost any momentum of filling up the pipe. We'd love to fill up the pipe with packets, especially when there's high latency, but we weren't able to do that. So we're about finished. We're going to have to not get into bytes in flight, but it'll be posted up on the website along with the captures. What I'm hoping that you walk away with is remembering that each side is independent, right? They make their own decisions, they have their own timers, and yet they're influenced by what the other side sends to them. And in some cases, what they don't send, because if they don't send, then certain timers kick in to change the TCP behavior. The visualization of seeing packets move across the network, do you find that useful to kind of help help see, okay, it's now there's a round trip involved, and I sent 3, I got back 2. Do you find that helpful? At all. I don't think I could do as many engagements as I do without that visualization. So I use the combination of Wireshark with profiles and RTT and then the visualization to help me explain to the customer. Because I can't take summary level decodes to most of the customers and say, here's the answer. But if I can show them a picture, they go, oh, I think I got this now. Especially like a picture of retransmit timeout that doubles every time, and then you see finally the connection resets. Pictures like that are super meaningful when you're trying to explain to a non-technical audience. Like sometimes my customer is the network guy, but sometimes it's his or her boss, or his or her boss, whoever paid for the engagement, because they want to know, why did I pay for this? What am I getting, right? So the rest of this, and any other comments? And then we're going to go to the thank you page. Yes?
I've had cases where disabling the offloads improves the performance.
Yeah.
Because I think sometimes it's that the operating system doesn't understand what the network card is doing.
So I just want to repeat that because that's a key point. So the comment was sometimes we've seen performance improve when we turn off segmentation offloading, because the OS doesn't know that the NIC card is doing special magic, or the special magic that the NIC card is doing is actually not helpful. It could be a bad version. If you think about upgrading drivers on your operating system, sometimes there's NIC card driver updates. Well, what are those? Sometimes those are changes to things like segmentation offload to repair bugs. So you don't necessarily think about the NIC card as having a processor and doing work and even a mini TCP stack, but it does. And it has to work in concert with the operating system. So when this gets uploaded, you'll see the next section is bytes in flight. There's no time in this session to walk through it, but it is hopefully interesting. There's some great graphics of bytes in flight overlaid and some more explanation, and then wrap up and summary. So from my own personal experience, there's been an evolution of believing what I understand about TCP. I used to think, oh, I got this concept, and then I'd see something new that challenged that belief. It's like, no, I don't really understand it as well as I thought, which made me go deeper, because I really want to feel confident that I understand the fundamental concepts. So it can be confusing, especially with high latency. If you have both captures, it's beneficial, and you do need to somehow be comfortable saying, okay, now I'm going to focus on what the client, what I think the client sees and it believes versus what the server sees and what it believes. Lots of great features. I love profiles. I love the developers. Please use the help documentation. And if you find it confusing or you think it could be better, let the developers know and they'll update the man pages. They really will. Visualization can help. Advanced analytics are icing on the cake. So thank you. I hope this was worth the time. I think we're looking at things that may be deeper than expected, or maybe I'm hoping that at least some of the concepts you walk away with are helpful. There is a section at the end for latency and congestion where we're comparing both sides yet again. So thank you all. Enjoy the rest of the session.